I'm RKA, and I'm an idiot. Today I want to idiotize about space and time, or rather, the quantization of space and time. And we'll start at square one, the speed of light. Speed means distance over time.
You may remember that in my little universe, a photon is like a kangaroo that hops and hops and hops from space cube to space cube at a constant rate, covering exactly the same distance all the time. How can a photon be so precise? I mean, not all photons are bright, really. Well, as I mentioned in a previous episode, in my little universe, space is quantized. It consists of little space units, which first I called space bubbles, and then I changed to space cubes because I didn't know what to do with the space in between the bubbles. And if you use space cubes with sharp edges, you don't end up with space in between. So this quantization of space explains why the distance that a photon covers with every single hop is constant all the time. But what about the disadvantages of space cubes versus space bubbles? Have a look at the drawing at the bottom. A photon travels through 4 space cubes transversely from left to right, and it covers the distance 1. The photon 2 travels obliquely through space cubes 1 to 4. You can see the drawing up left. And it covers distance 2, which is obviously longer than distance 1. Does that mean photon 2 is faster than photon 1? Of course not. Have a look at the drawings at the bottom. On the left side you see an animation of our solar system. On the right side you see an animation of an atom. The animation of our solar system is kind of realistic. The animation of the atom has nothing to do with the real atom. I think it's time to introduce a new concept, the concept of space units rather than space cubes or space bubbles. Space units are purely functional. They don't have a macroscopic shape or size or dimension. So it doesn't matter whether we use bubbles or cubes to symbolize them. The distance between 2 space units is called a space quantum. A space quantum is a distance, so it can be measured or at least calculated. I think it's about time to talk about 2 worlds, the micro world and the macro world. Let's start out with the macro world, which is more familiar to most of us. The macro world is an aesthetic world, which does not mean it has anything to do with plastic surgery. It means it's a world we can experience with our senses. We can taste it, we can smell it, we can feel it and see it and hear it. It's a natural world. Even animals can experience the macro world. It is structural and concrete. When we talk about the physics of the macro world, we think of Sir Isaac Newton. Mathematically speaking, we talk about Euclidean geometry and simple algebra. Technically speaking, we talk about hardware. In my little universe, we talk about macro facilitation. The micro world is totally different. It's an artificial world. It's been invented by human beings such as Bohr, Heisenberg and Schrödinger. It's abstract and functional. Animals don't know the micro world, as far as I know. Mathematically speaking, we talk about wave functions and statistics. Technically speaking, we talk about software. And in my little universe, we're talking about microfacilitation. Now, where do space and time come from? How much is a quantum of space? How much is a quantum of time? At the beginning, there was the Big Bang. The Big Bang created matter and space and electromagnetic waves. The interaction of matter and space, or electromagnetic waves in space, created things like mass and gravity and inertia and time and entropy. In my little universe, things are very simple. Hey, I'm an idiot. Initially, there was the Big Bang with its primordial energy. And this primordial energy was then transformed into electromagnetic waves and into matter and into space. Every transformation increased entropy. So space is a kind of energy with the highest degree of entropy. In the end, electromagnetic waves, matter and space all end up in a big black hole and get recycled to primordial energy. So now we know where space comes from, but we still don't know what is space. What is space? Simple as it may sound, this question is actually very difficult to answer, and if you look it up in various dictionaries, you'll get all sorts of fancy answers. Very often we define space by objects at the edge of the space. The space of a building is defined by its walls, for instance. In my little universe, space is sort of in between the micro world and the macro world. Space units belong to the micro world, space quanta to the macro world. So what is space in my little universe? In the micro world, space consists of space units. Space units consist of energy with the highest possible degree of entropy. These space units interact with matter and electromagnetic waves. When a photon hits a space unit 1, it causes all sorts of effects through interaction. One of the effects is that space unit 1 sends out information to its neighboring space units. It's very much like dropping a stone in the pond. So in my little universe, space is a three-dimensional grid. It's absolute and cannot be twisted or bent like in the Einsteinian universe. It consists of space units, and space units are things of the microscopic world. They have no macroscopic shape, they're functional. They harbor a software which then creates all sorts of effects, like the electromagnetic field, the Higgs field, the gravitational field, etc. What about time? In my little universe, time has something to do with the transformation of energy. Objects like matter or electromagnetic waves constantly interact with space units. This leads to a transformation of energy, to an increase in entropy, and to the creation of time. No object, no time. Empty space does not create time. There is no universal time. Time is not a dimension. Time is not just there, it is constantly being created. Every interaction of a particle of matter or a photon with space units results in an increase in entropy and the creation of a time quantum. This time quantum sticks to the particle or photon that caused its creation. Imagine we could create a flashlight which sends out photons at double the speed of light. The blue flashlight sends out photons at the speed of light, and such a photon hops and hops and hops through 4 space units and creates 4 units of time. The red photon hops and hops and hops, and it covers 8 space units, but it creates 8 time units at the same time. So, no luck. You cannot double the speed of light. When a photon P interacts with space unit 1, it loses some of its energy, and it travels on as P prime, which has less energy than P, plus an extra quantum of time, which will stick to P prime for the rest of its life. Space unit 1 uses the energy of P and creates a space unit 2. So in my little universe, when a photon crosses the universe, it interacts with space and creates new space, and thus loses energy. This causes redshifting. What's interesting is that it's not the frequency of a photon that decides how much time is being created when the photon interacts with a space unit. So the speed of light is the same for a photon at a frequency of 10 to the 20th per second as compared to a photon with a frequency of 10 to the 10th per second. Now, what about energy? Suppose a photon has traveled for 10 billion years and it has covered 10 billion light years. It has crossed X space units. Let's assume it started out at a frequency of 10 to the 20th per second. This correlates to a wavelength of about 3 times 10 to the minus 12 meters. Let us assume that after traveling for 10 billion years, the photon has redshifted with a redshift parameter of z equals 2. What does this do to the energy of our photon? Well, I left school more than 40 years ago, so my calculations might be wrong. I hope they are not. If they are not, this photon had an initial energy of 6.6 times 10 to the minus 14 joules, and it lost 2/3 of that energy, which is 4.4 times 10 to the minus 14 joules. In my little universe, this redshifting is due to a tribute that every photon has to pay when it interacts with a space unit. As a receipt, it receives a quantum of time for every interaction. These quanta of time stick to the photon for the rest of its life. So, if I'm not mistaken, our photon has traveled 9.46 times 10 to the 25th meters in 10 billion years, which means in 3.15 times 10 to the 17th seconds, and it has lost 4.4 times 10 to the minus 14th joules. Our photon has traveled 9.46 times 10 to the 25th meters, which correspond to n space quanta. It has aged by 10 billion years, which correspond to n time quanta. And it has lost 4.4 times 10 to the minus 14th joules, which correspond to n energy quanta. So n space quanta correspond to 10 billion light years. What if a space quantum had Planck length? In the Gaussian version, this would be 1.6. In the Lorentz-Heaviside version, 5.7 times 10 to the minus 35th meters, according to Wikipedia. If I'm not mistaken, and this might well be, hey, I'm an idiot, n would be 6 times 10 to the 60th, according to the Gaussian version, and a third of that according to the Lorentz-Heaviside version. This means 10 billion light years correspond to 6 times 10 to the 60th space units, if you use the Gaussian version of Planck length. Now let's try the same thing with the time. Using the Gaussian version, I end up with the same number of time quanta. Surprise, surprise. The Lorentz-Heaviside version gives me a different result when I figure out the number of time quanta versus the number of space quanta. Since I like it simple and stupid, I've decided to stick to the Gaussian version of Planck units. When we look at the energy side and we look at Planck energy units, then we end up with bizarre results. The unit of Planck energy is way too high to give any reasonable result in my little calculation. Based on Planck energy, a space unit would be much bigger than 10 billion light years, which makes no sense at all. So let's try and figure out ourselves what an energy quantum might be. I mean, we've got the number of n's, and we've got the total amount of delta E. So, in my little universe, the winners are 1 space quantum equals 1.6 times 10 to the minus 35th meter. 1 quantum of time equals 5.4 times 10 to the minus 44th seconds. 1 quantum of energy equals 0.7 times 10 to the minus 74th joules. Of course, these are not precise figures, they're rough estimates based on a redshift parameter of 2, which of course is not very precise. Please notice that we've now talked about the interaction of a photon and a space unit. The interaction of space units and particles are different. We'll talk about that later. We can now complete our little drawing about the interaction of a photon P with a space unit 1. The photon P loses with every interaction with a space unit 0.7 times 10 to the minus 74th joules. And it earns a time badge, which it will never get rid of. Space Unit 1 uses the energy and creates a Space Unit 2. Let's go back to our question, what is time? A photon 1 with the energy x and an entropic factor y interacts with a space unit, and it ends up as a photon 1 prime with less energy, a higher entropic factor, and a quantum of time. The space unit uses the energy that photon 1 gives up and creates another space unit. So time in my little universe comes with a change in entropy. And you may remember that entropy in my little universe is the sum of all potential differences at the beginning of our universe divided by the sum of all potential differences now. Time is not a pre-existing fourth dimension. Time is being created when electromagnetic waves or matter interact with space. This interaction limits the speed of light and everything else. Black holes convert electromagnetic waves, matter and space into primordial energy with no entropy, and thus eliminate time.